Hey guys, so this is my second video and be talking about the difference between general and special relativity, because this is a sticking point I find for a lot of physics students. Okay, so firstly, general relativity refers to a geometric description of space-time, our space-time continuum, and postulates that in the presence of a mass or an energy, so a mass does have energy, that space-time itself is not flat or linear, and rather it is observed as warped or curved due to the influence of gravity, which is induced by the existence of these objects or object which possesses mass and energy in the first place. So the fact that it exists in this space-time, and that's what we're viewing as the curvature of space-time, is the gravity which is induced by this object of mass. So, in other words, gravity caused by the mass or the object that has energy is the curvature of space-time, and its influence will depend upon where we draw our measurement relative to that curvature. So where along that curvature are we drawing our measurements from, and we account for these influences of the curvature in space-time by introducing forces such as the Coriolis force or the centrifugal force. When using general relativity to assess a situation, I should be more specific, and we are using general relativity as opposed to special relativity, we need to make our calculations with an accounting for the fact that our space-time is non-linear, and we do so by curving space-time by introducing these Coriolis, centrifugal / fictitious forces. Basically, to sum that up, what we're saying is we're going to actually account for the change, the influence that object with mass and energy has on space-time, as treating space-time to be curved in itself. So, that's general relativity. Special relativity, on the other hand, refers to a way of making calculations regarding our frame of reference, so our space-time, where, unlike in general relativity, space-time is in fact viewed or observed as linear or flat. And these reference frames themselves, because of this, expand and contract in order to account for the differences in velocities or distances of the reference frames relative to one another. So we can't just throw the discrepancy out the window that in different parts of, or in different references in space-time, things behave differently. We have to account for that somehow, but we either account for it by having the reference frame itself, the space-time continuum itself, be affected, be curved in general relativity, or we treat the reference frames as linear, so non-curved, but we account for a discrepancy between one another. So that's what I mean by these reference frames expand or contract in order to make up for that, the fact that we're allowing them to be linear in special relativity. And because of this, because they are linear, we don't have to solve the problems using special relativity, we don't need to introduce those fictitious forces I was referring to in general relativity, such as the Coriolis force or centrifugal force, because we're accounting for them with this expansion and contraction, and accounting for their relativities to one another, these reference frames being relative to one another. And by doing so, what I wanted to elaborate on is, by doing so, that allows us to have the laws that govern objects that we've learned up until this point, the laws of physics that govern behavior of objects. It allows them to remain constant throughout reference frame to reference frame. So it allows our laws to be legitimate and throughout each reference frame, constant in each reference frame. The reference frames themselves will just be different relative to each other, but the behavior within the reference frames will be able to be evaluated similarly from one reference frame to the next. And this exact, outcome of that factor is what allows the speed of light, so usually denoted with the letter C, and it's 3 times 10 to the 8 meters per second. It's the velocity of speed of light. It allows the speed of light to remain constant, remain that magnitude, 3 times 10 to the exponent positive 8 meters per second. So it allows it to remain constant regardless of the reference frame, just like it allows behavior, the laws that govern behavior, to remain constant within the different reference frames. We just have to make the reference frames relative to one another. So if we have an event going on at one place in space-time and another event going on in a different place in space-time, or the event itself is happening at a much greater velocity than that of the original reference frame we were referring to, we have to have a way to account for that, and we do so while continuing to treat space-time, so our reference frames, as linear themselves. We don't introduce these fictitious forces of Coriolis or centrifugal, anything like that, in order to curve our space-time and make it non-linear. We're still dealing with linear reference frames, meaning that the coordinate system that we use in special relativity is the XYZ axis, or if you want to deal with polar coordinate axis, it's fine as well, but they're all 90 degrees to one another. There's no curvature. But we still have to have a way to account for the differences, like I said, in velocities or distances when they approach greater magnitudes between one or more reference frames. So we do so by physically contracting or expanding the reference frames themselves so that they have relativity to one another. So I will give some examples to highlight the difference between what would happen if we use general relativity to assess and make calculations about a scenario, and then how we would approach it if we were going to employ special relativity. And it's given as an example of billiard balls. So if you've ever played pool before, they're the balls that you use for the game. And we pretend that we have two scenarios, one in which we're going to play this billiard game, play a game of pool on a regular pool table, which has a completely flat linear surface. So remember, special relativity has our reference frame, our space-time being flat. And then if we were to play the same game of billiards, the same game of pool, but now on a mattress. So mattresses have springs, and they can depress when they have weight placed upon them. So we can see how if we played this game of pool on the hard, flat, linear surface of a regular billiard ball table, that the action of the ball that we were hitting with a pool cue would be unaltered by the presence of other balls or weights around it, because that linear surface would not depress, so not allow that curvature or depression to happen. So that is parallel to the concept of how in special relativity there isn't a curvature of space-time because of that linear surface. Whereas if we played the same game of pool on the mattress, which does in fact depress, the behavior of the motion of the ball getting hit by the pool cue would be affected by where the other ball's weights were placed around it, because those weights would cause a depression in the mattress, i.e. they would give way to gravity in our space-time continuum, which would be the curvature of space-time. So since their weight giving rise to gravity would bend the mattress, this is sort of a metaphorical comparative bending of our space-time for the example of, for the employment of the concept of general relativity in this example. So mattress bending, space-time curvature, versus the hard flat surface, which is the employment of special relativity to solve the same example. So hopefully that clears up the difference between the two concepts, special and general relativity, and thank you for watching.